Hello everyone and welcome back. So today we're going to be going over the principle of linear impulse and momentum, as well as conservation of linear momentum for systems of particles. Now as a note, particles are magic. They can be the size of a train or as small as a piece of dust. So when I say particle, don't think just tiny things. They can be huge too. Okay, so linear momentum is what we're going to be caring about today, and understand how conservation of momentum works. So some applications of this. One example is this ball right here. We have this ball shooting machine. And how does it work? Well, it works by having these two wheels rotate very, very quickly. And the friction between those two, the wheel and the ball, causes that ball to propel forward. Now, it is in contact with the ball for a very short amount of time. And so if we're looking at its velocity directly after it has moved, just in that instant after it's moved, that is not going to be really affected by its weight all that much. It's not really an impulsive force. But these forces right here are going to be much, much larger, and they're going to be controlling the direction of the ball. So one question might be, does the release velocity of the ball depend on the mass of the ball? And the answer is yes. Yes, it does. Another one like here. This is a crane-mounted hammer, which is used to drive piles into the ground. And we can figure out how deep it's going to go into the ground and how high the hammer would have to go to get it there using conservation of momentum. Now, we have to make some assumptions. One, that it does not rebound, because that's not good. Just a little detail here. If you want to make sure that you survive getting hit in the head with a brick or something, you don't want that brick to rebound. That's a bad sign. So if it smacks your head and sticks, you're in a better situation. Best of yet, just avoid the brick entirely. Just avoid the brick. Don't get hit in the head with a brick. Cyrano de Bergerac had that happen to him. No fun. So if the hammer rebounds, how is that going to change the effect of it falling and hitting the stakes? What's going to happen with that? Also, where are our resistive forces? Do we need to include them, like the ground? How about that? What about the weight of the pile? Is that something we have to consider? So all these things we have to take into account and figure out which ones are important and which ones aren't. So now we're looking at this for a system of particles. Now, as with our internal forces, our internal impulses all sum to zero. We don't care about the individual impulses of them. It's the system that we care about. Now, using that, we can then say, okay, with that, we can now say, okay, all my individual particles, the sum of their momentum, plus the sum of the external forces acting on them, the impulse from those external forces, is going to equal to the sum of momentum at the end. Now, normally it's not particles. Think trains, think cars, think a child jumping onto a sled, something like that. Those are the things that are going to be helping you out here. Now, all of these are going to move together. However, are they all moving in the same direction? Well, not necessarily. And that's where it gets a little bit weird here. Like, okay, all these particles are not moving in the same direction, so what's moving? Well, what you do is you find a fictitious center of mass for this particle. You kind of add them all together. And then you can find out that this center of mass will have a aggregate velocity. We're adding all the velocities together. When we do that is we take their total momentum and we divide by the total mass to get the overall velocity of the group of particles. Okay? And we can also find the center of that as well to describe the motion of the center of mass. Now, interestingly enough, when the sum of our external impulses acting on a system is zero, then we simplify this to conservation of momentum. So this is an amazing equation. I really, really love it. It's really good for collisions where, yes, there are forces happening, but those are all internals. Like if I have a car and it runs into another car, well, these are now two particles, and the force that's going to be exerted from them when they collide is going to be an internal force. So overall, the motion is not going to be determined by that force. It's going to be determined by their overall masses and velocities. So with this, it can be very, very helpful. For example, if we look at this sledgehammer right here, it's applying an impulsive force to the stake. Now, we know that the weight of the stake is considered negligible as compared to the force of the sledgehammer. And if that stake is driven into the ground with little resistance, the impulse of the ground acting on the stake is considered non-impulsive. So what does that tell us? Well, then if we look at the stake and the hammerhead as a system, we can say, okay, well, that impulse is an internal impulse, and we can simplify it down to this. Because there's nothing else acting on it there. It's just these two forces that are controlling the motion, at least for that initial moment. Okay, the ground is going to do it eventually. Weight's going to have effect after that. But for that instant, its motion is going to be just the conservation of momentum equation. Oh, so we'll stop there, and next time we'll jump into an example of this. So thank you for listening. I hope this helps you. This equation right here, just going to put some arrows to it. Some arrows, no apparent reason for that, just, love drawing arrows. Definitely not going to be helpful anytime soon. Okay, that's enough for now. So, have a good day. See you later. Bye-bye.